In this video, you're going to learn an extension of the concept of percent composition and also one more helpful conversion factor when dealing with molecules and atoms and moles and things like that. First off, when talking about percent composition, what we're really talking about is the percent by mass. So when we say that water has a percent composition of 11.2% hydrogen, what we're really saying is that there are 11.2 grams of hydrogen in every 100 grams of water. So the thing I want you to notice here is that it is a mass percent that we're talking about. We're talking about the percent by mass of hydrogen, so of that element, in 100 grams of the entire molecule or compound. So when we're looking, for example, at a problem that says how many grams of hydrogen are in 36.2 grams of water, we're going to utilize this information of percent composition. So we know that there's 11.2% hydrogen by mass in water, which means that there are 11.2 grams of hydrogen in every 100 grams of water. And that's where we're getting this percent sign from, is 11.2 grams in 100 grams of something. So when you're given 36.2 grams of water, and we're trying to determine how many grams of hydrogen are in that, we can use this percent composition as a conversion factor. So we can see that there are 11.2 grams of hydrogen in every 100 grams of water. And again, it's this amount over 100 that is really giving us that percent idea. So that's where that percent composition is coming from. And so if we were going to do this calculation out, you can see that grams of hydrogen would cancel out, leaving us with, grams of water would cancel out, leaving us with grams of hydrogen. And if you calculate this out, I got 4.05 grams of hydrogen. And I'm rounding this number to 3 significant figures because there are 3 sig figs in the given. So 4.05 grams of hydrogen in 36.2 grams of water. So that's the extension of percent composition that I wanted to explain to you. Now let's take a look at the conversion factors that were useful in this chapter. One conversion factor that we talked about was the fact that 1 mole of something is equal to 6.022 times 10 to the 23rd atoms or molecules or formula units. And the second one that we used quite extensively was going from grams of something to moles of that same thing and back. And remember, we called this molar mass. And that number of molar mass always ended up with the grams in the conversion factor. And we always put a 1 in front of mole in the conversion factor because by definition, molar mass is the mass of 1 mole of something, of just 1 mole of something. Okay, another useful conversion factor is understanding that in 1 molecule of something, there's a certain number of atoms. For example, let's talk about 1 molecule of carbon dioxide. In 1 molecule of carbon dioxide, there are 2 oxygen atoms. So going back and forth here can be a useful conversion, and that's what I wanted to concentrate the last part of this video on, was this very last conversion factor. Being able to talk about a part of a molecule and using that as a conversion factor. So the problem I gave you says, use the information you just wrote to help you determine the number of oxygen atoms in 12.3 grams of carbon dioxide. Now using molar mass, we can convert grams of carbon dioxide into moles of carbon dioxide. And remember, we call this thing right here molar mass. And then from there, we know that we can convert moles of CO2 to molecules of CO2. And the very last thing is this last conversion factor, where we can change molecules of CO2 into oxygen atoms. Now let's go ahead and fill in the numbers. The molar mass, this part right here, of carbon dioxide is 44.01. So 44.01 grams of carbon dioxide is equal to 1 mole of carbon dioxide. We also know that 1 mole of carbon dioxide is the same as 6.022 times 10 to the 23rd molecules of carbon dioxide. Now this new conversion factor, we know that 1 molecule of carbon dioxide has 2 oxygen atoms in it. So that's what our dimensional analysis is going to look like. And if you calculate this all out, I got 3.37 times 10 to the 23rd oxygen atoms as my final answer, with the right number of sig figs. Our given here has 3 sig figs, and you'll notice I rounded this answer to 3 sig figs as well. Okay, now on this practice on your own, it says how many hydrogen atoms are in 26.7 grams of hydrogen peroxide. The first thing that we need to know there is what the percent composition of hydrogen is in hydrogen peroxide. So figuring that out, I figured out, or sorry, we don't need to know the percent composition for this one. We're going to start with 26.7 grams of hydrogen peroxide. We know that we're allowed to change grams of hydrogen peroxide into moles of hydrogen peroxide, which is just the molar mass. We also know that we're allowed to change the moles of hydrogen peroxide into molecules of hydrogen peroxide. And then finally, we're going to change molecules of H2O2 into hydrogen atoms, because that's what it was asking for, was the actual number of hydrogen atoms within 26.7 grams of hydrogen peroxide. Now let's go ahead and fill in the numbers. The molar mass of hydrogen peroxide is 34.02 grams per mole. We know that 1 mole of hydrogen peroxide represents 6.022 times 10 to the 23rd molecules of hydrogen peroxide. We also know that 1 molecule of hydrogen peroxide has 2 hydrogen atoms in it. So that's what our dimensional analysis looks like. I know it's kind of squished on there, but if you calculate this out, I ended up with 9.46 times 10 to the 23rd hydrogen atoms as my final answer. The next problem here says how many grams of hydrogen are in 26.7 grams of hydrogen peroxide. So here they're asking us about a mass within a mass. That's how we know we're going to use percent composition. So the percent composition of hydrogen in hydrogen peroxide, if you calculate that out, I got out that there was 5.94% hydrogen by mass in hydrogen peroxide, and I did that by figuring out if 2 hydrogens represents 2.02 grams per mole and 2 oxygens represents 32, and the mass of the whole thing is 34.02, and I just took the 2.02 for hydrogen and divided it by the whole thing and multiplied it by 100 to get the percent by mass of hydrogen. So in this problem we have 26.7 grams of hydrogen peroxide. Now we know that there are 5.94 grams of hydrogen in every 100 grams of H2O2. So that's what our dimensional analysis looks like. And those will go away and we'll end up with grams of hydrogen. When I calculated this out, I got 1.59 grams of hydrogen as my final answer. Now in that last problem there, it says, how many oxygen atoms are in 26.7 grams of hydrogen peroxide? We know we're going to be using that new conversion factor because it's asking us specifically about a certain atom within a whole molecule. So we know that 1 molecule of H2O2 is the same as, or has in it, 2 oxygen atoms, and it's that conversion factor that we're going to use. So let's start out with 26.7 grams of hydrogen peroxide. We're going to change that grams of hydrogen peroxide to moles of hydrogen peroxide. Then we're going to change the moles of hydrogen peroxide into molecules of hydrogen peroxide. And finally, we're going to change molecules of hydrogen peroxide into oxygen atoms and use that conversion factor. So we're going to use this conversion factor right here. Now let's go ahead and fill in what we know. This part right here, remember, is the molar mass. So the molar mass of hydrogen peroxide is 34.02 grams per mole. We also know that 1 mole has in it 6.022 times 10 to the 23rd. And we know that 1 molecule of hydrogen peroxide has 2 oxygen atoms in it. So that's what our dimensional analysis looks like. And if you solve this out, I got out 9.45 times 10 to the 23rd oxygen atoms as my final answer. So hopefully you got out the same thing when you did this.